Hi everybody, welcome to Chapter 4, Lesson 1. And we're going to talk about water and why it's so valuable to us. And I want to show you a short video clip related to that. So here we go.
Life is based on water, primarily because of water's solvent properties. Understanding this and the other properties that make water so important means understanding water's molecular structure. Any molecule can be represented in several ways, each having particular advantages. Molecular formulas, for example, are compact and indicate the number and identity of atoms in the molecule. Structural formulas show the bonds between atoms. Ball and stick models take up more space than structural formulas, but include information about bond geometry. Space-filling models are not as easy to read as ball and stick models, but they depict the spatial relationships between atoms more accurately. Water is a solvent for many of the molecules in living organisms, primarily because it's a polar molecule. The oxygen atom in the water molecule has a high electronegativity. This means that electrons shared by the hydrogen and oxygen atoms are more attracted to the oxygen than to the hydrogen. This unequal attraction of electrons generates partial electric charges within the water molecule. The oxygen atom has a partial negative charge, and the hydrogen atoms have a partial positive charge. Therefore, a water molecule as a whole has positive and negative ends. The molecule is polar. When two liquid water molecules approach each other, the partially negative oxygen atom of one water molecule is attracted to the partially positive hydrogen atom of the other water molecule. Hydrogen bonds form between water molecules, causing them to stick together. These same hydrogen bonds form between water and other molecules that carry charges. Here's an example of how water acts as an efficient solvent of table salt or sodium chloride. Water molecules surround the sodium and chloride ions of salt. The oxygen atom in each water molecule, with its partial negative charge, bonds to a positively charged sodium ion. The hydrogen atoms of the water molecule, with their partial positive charges, bond to the negatively charged chloride ions. Water's polarity makes it an effective solvent for charged or polar solutes. The hydrogen bonds that form between water molecules are responsible for one of water's most unusual properties. Although solids are usually denser than liquids, water expands and becomes less dense as it changes from a liquid to a solid. This property allows ice to float on water. Let's examine why ice floats on water. In ice, each water molecule forms 4 hydrogen bonds with 4 adjacent water molecules, giving the ice an ordered lattice structure. In this structure, the hydrogen bonds overcome the motion of the individual water molecules, holding them in a fixed three-dimensional pattern. In addition, the water molecules are spaced farther apart, making ice less dense than water. As ice melts, hydrogen bonds are broken, and the water molecules are free to move closer together, forming liquid water. Liquid water, therefore, is more compact or denser than ice. What would be the implications for life if ice were denser than liquid water?
Okay, so hopefully you picked up from the video the idea that water is great, and it's great because it is polar. And so let's talk a little bit about why it's polar. We know that water has many properties, like it regulates the earth temperature, it cools automotive engines, it cools nuclear power plants. It's pretty much fantastic. It can dissolve a whole lot of things. And again, the reason it can dissolve is because it's a highly polar molecule. Now, molecule polarity is determined by 2 things. It's determined by bond polarity and the distribution of the partial charges. So the fact that it's a polar molecule is for 2 reasons. It has, number 1, polar bonds. Let's talk about those first. Bond polarity is determined by electronegativity difference. If we look up the electronegativity of oxygen, it's something like, I don't know, 3.5. If you look up the electronegativity of hydrogen, it's 2.1. So as you saw in the video, within the bond, the electrons are not being shared equally, because think of electronegativity like a strength, a force. And oxygen is pulling on those electrons with the strength of 3.5, and hydrogen is pulling on those electrons with the strength of 2.1. So the electrons in this bond, I'll draw them in red, are going to end up closer to oxygen. Those are your electrons. So the electrons in this bond are going towards oxygen. That's going to be the same thing in this bond. The electrons in this bond are being shifted or drawn towards oxygen. So there's a high electron density around oxygen in this molecule, which is not canceled out by any other bond. And as a result, oxygen gets a partial negative, and the hydrogens get partial positives. And those do not cancel out. So the molecule is polar because, number one, it has polar bonds, and number two, the shape of the molecule lends itself so that those polar bonds are not canceling each other out. So because of its shape, the molecule remains polar because all of the electrons go towards oxygen. All of the electrons here go towards oxygen, and there is no opposing pull or draw of electrons. So water can dissolve a lot of stuff because of its high degree of polarity, okay? If you flip to the second page of your notes, there's this idea of hydration. And hydration is really just what happens during dissolving. Whoops. Okay? And really what it is when the negative part of water, which is oxygen, gets attracted to the positive part of the salt, which in this case is sodium. So you can see here in this picture that oxygen, which is negative, is attracted to the positive sodium ions in the salt, and it pulls it away from the chlorine. And the opposite can also happen. The positive part of water, which is hydrogen, gets attracted to the negative ions in the salt. So that is why dissolving occurs, is because water is actually able to pull the positive and negatives away from each other in the salt. And I have another animation of that I'll show you here. Let me just reset this and move this over. Okay, this one does not have sound. But what you can see is the red, which is oxygen, that's negative, is pulling away the positive ions in the salt, the little gray ones, the metals. One more time. And the white part, which are the little hydrogens, are attracting the large negative anions of the salt. And the salt's still there, the particles are still there, they're just pulled apart, so they're too small for us to see. So we'll take a look at the close-up view of the hydrogens attracting the negative there, okay? One more time. The hydrogens, which are positive, align themselves to the negative anion. And you can also see, if we do the oxygen here, the large oxygen negative is attracted to the small positive metal cations. They are hydrating those ions. So this hydration is also known as dissolving or dissociation. And what it means to dissociate is when the ionic compound breaks down into individual anions and cations. So for example, if NaCl is dissociating, it dissociates into Na+, and we say aqueous, and Cl-. If it's calcium chloride that's dissociating, it breaks down into one calcium ion, and notice what I do with this subscript, 2 chloride ions for every one calcium chloride that dissociates. So the subscript then becomes the coefficient, unless it's a polyatomic, something like say we had CaNO3 dissociating. It would dissociate into calcium plus 2 and then 2 nitrate ions. Okay? So the polyatomic doesn't break apart, but however many of that you have becomes then the coefficient. Okay? So dissociation is really the same as dissolving. It's just the breakdown of the ionic compound into individual ions. And recognize that these would be surrounded by water molecules. The calcium would have the oxygen of water all surrounding it, and the nitrate would have the hydrogen of water all surrounding it. Okay. Another example is ammonium nitrate dissolving in water. We can write the dissociation reaction or the dissolution reaction as NH4NO3 solid. We do not include water as part of the reaction in a sense that we do not write it as a reactant. But since we're breaking this down into the ions that compose ammonium nitrate, the ions are ammonium and nitrate. They must have the charge. And to show that water is present, we just include the AQ symbol, the aqueous. So we break that salt, that ionic compound down into the individual ions that compose it. Okay? Solubility is defined as how well something dissolves, and the general rule for solubility that I know you've heard of before is like dissolves like, which means polar things like water will dissolve other polar things like alcohol or ammonia is also polar. But non-polar substances like, say, oil or carbon tetrachloride will dissolve non-polar substances like, say, dirt, grease. Other things like that. Carbon dioxide. You can also have polar things like water dissolving ionic things, okay? Metal to non-metal. So the big joke is, what kind of bear dissolves in water? And I don't know what kind of bear dissolves in water. A polar bear, because like dissolves like. Water is polar and it will dissolve the polar bear. Solutions are what you generate. Solutions are what you generate when you have stuff dissolved in water. And the solvent, the thing that's present in the greater amount, does the dissolving. And in most cases, and especially in this chapter, that will be water will be our solvent. And it's such a good solvent because it's polar. And the thing that gets dissolved is the solute. And when you take the solvent and you dissolve the solute in it, we assume complete dissolution. We assume a uniform distribution, which means that all solutions are homogeneous mixtures. The parts of the solute are uniformly distributed in the solvent. Okay? So when table salt is mixed with water, the salt is still there. You can get it back by evaporating the water. The solvent is water. It's present in the larger amount. The solute is salt. It's present in the smaller amount. Okay, I think we'll pick up with part 2 with this idea of electrolytes and non-electrolytes, and we'll do a little demonstration with this in class tomorrow. So we'll pause for now and come back with part 2.